get going.
Let's get going. Huh? So first, let me thank you all for coming to our Chemical Engineering Technology Capstone presentations. This is the 11th one we've done. Yeah, I added it up. It's 11. So this is going to be a great one. The students have been working very hard. So at least that's what I've heard. And so I'm going to be excited to hear what they have to say. I want to particularly thank our advisory board members for coming, our folks who are our company representatives who support us so well, and we have administrators here, we've got family members here, we've got students here, so listen up and let's hear what they have to say. And first I'll introduce our Professor Dave Chekla, who's been working with the students all semester. So Dave, why don't you take it away?
Thank you. Yeah, it's been a pleasure working with these groups. As many of you are aware, we have 2 cohorts and 3 presentations tonight. There's a common one for both cohorts, which we'll present first. And then we'll get into a couple of other presentations with the individual cohorts. Just want to say thank you to Laura and everybody for putting all this together. We had good news. I don't know if you brought it up. We got our accreditation this year. So Professor Laura, let's give her a round. And Professor Linda, I know, is her right hand on a lot of that stuff. And so congratulations. And all our adjuncts were all happy to help. So, but they did the brunt of the work, and it was awesome. So I just wanted to say that. That being said, we'll go ahead and get started here. As I said, we have 3 presentations tonight. We have one on distillation, chemical reactors, and friction loss and piping systems. All 3 presentations are laid out pretty much the same way, as you can see by the agenda there. We'll go over some project plans and goals. We'll go over a little background theory, present our experiments and our experimental results, and go through our little discussions and conclusions, recommendations, lessons learned, and we'll have a short Q&A after each presentation. At this point, I'd like to introduce our day cohort, if they would come on up and introduce themselves.
My name's Alan Cox. I like fishing, golfing, and I'm here to hopefully have a future career.
My name's Oscar. I enjoy spending time with my wife and my kids. I enjoy playing golf. I'm hoping to get out of the program to develop the skills and education needed to start my career as an operator.
Hi, my name is Chandler Dukes. In my free time, I like weightlifting and hiking, as well as hanging out with friends. And the reason I chose this program was to have a steady job and a good career for my future.
My name is Chastin Henry, and one of my hobbies is blues coaching softball. I joined the program to obtain a stable career after graduation.
My name is Cole Hines. I played baseball here at Roane State for 2 years, and I joined this program because my advisor said it was a good route.
My name is Brandon Keeble. Currently doing auto body, and I hope this program prepares me for the workforce, leading to a smooth and successful career.
My name is Joshua Owen. I like to play golf, watch golf. I really joined this program to have me a better plan for my future.
I'm Joe Tipton. I like to golf and work out during my off time, and I chose this program to just get a steady job in the future.
I'm Hunter Townsend. I really enjoy the outdoors, and I chose this program because I thought it would be a great career fit.
Very good. And let's go ahead and I'll ask the day cohort to sit down, and let's go ahead and introduce the evening cohort.
Good evening, my name is Joshua Campbell. I'm currently a chemo apprentice at Y12 where I've been for about 4 years now. Now, I kind of hope to gain from this program a long and stable future in the chemical and nuclear industry.
My name's Andrew Kaler, also apprentice at Y12, been out there since 2019, married, 2 kids.
Hope this program has helped me in the future with my job.
My name is Jay Gielam. I like to fish and do a lot of outdoor things. I'm in this program because I've always liked science. I want to use it to start a strong life, and hoping that this program will help me with the ability to provide a future for my family and other members.
My name is Jericho Falligan, and I joined this program to culminate a career transporting chemicals up to hazardous waste. And I want to, change aspects of that and get with the company and work with the team so I can do my part in America to keep America, forefront of chemical and nuclear power.
My name is Isaac Hickey. I run cross country and track for Roane State. I joined this program because it seemed like a good opportunity for me and a good opportunity for the future. So,
I'm Dean Humphrey. I'm a chemical operator apprentice at Y12, and by completing this program, I hope to gain value as an employee in the chemical industry.
Welcome, my name is Chris McKinney. I've been at Y12 for 20 years. I've always enjoyed chemistry and troubleshooting, so I'm going to give this a shot.
My name is Carson DeLong. In my free time, I enjoy cooking with my fiance and solving puzzles. And I chose this program in order to get a firm foundation that I can use to find a job that I can turn into a long-term career.
My name is Cole Richmond. I'm currently a chemical operator apprentice at Y12, and by completing this program, I hope to gain skills and knowledge that will help me with my career. And in my free time, I enjoy riding motorcycles and hanging out with my dog, Seabass.
At this time, I'll ask some of the evening to sit down and some of the day cohort to come up here. We'll get into our first presentation for distillation. So we had originally planned to do distillation for both cohorts all semester long, and ran into a little issue with one of our controllers on our distillation system. And as you can see down there, we fried a wire pretty good and saw some smoke. And after some troubleshooting, we ended up deciding to pursue a couple other technologies because to recover would have been a little extreme to miss a few labs and then kind of make them up toward the end of the semester. So we chose a couple other technologies and went with it. As you can see up here, this was our project plan. Those things that are lined out are things we didn't get to work on, but we did run the system in 2 modes. Mainly looking at how parameters affect yield and production rate, and also perform material balances. We looked at further concentration of ethanol using molecular sieves, and where we could make some comparison between the modes of operations, we would. At this point, we'll introduce some distillation theory and background information.
Here is some distillation history. Some of the earliest evidence of distillation is in 3000 BC in the Indus Valley of Pakistan. In the 9th century, an Arab chemist, Al-Kindi, first distilled alcohol. By the 12th century, the distillation of beverages became common in Italy and China. Distillation is a process of separating a liquid mixture by using the differences of components to individual boiling points. We use a column to fractionate the liquids based on those boiling points.
So here are a few applications and products of distillation. One of the most common one is crude oil refining, where you can separate out products like gasoline, kerosene, and diesel. Alcohol purification sometimes is used in the food industry to increase concentrations in alcoholic beverages. Desalination is a very energy intensive process, but it can be used to separate fresh water from seawater. And cryogenic distillation is when you liquefy air under extremely cold temperatures to produce separate products like oxygen, nitrogen, and argon. So here are a few key terms to remember. We're going to be going into these in more detail later. Just keep an eye out for these. So we have fluid, latent heat of vaporization, vapor pressure, and phase diagram. Just some more key terms like boiling, fractionization, yield, production rate, and hydrometer. And like I said earlier, we're going to be going over these in more detail later.
So first we're going to cover 3 terms. The first one is latent heat, which is the amount of heat energy required to be added or removed to create a phase change. Then we have latent heat of fusion, which is the amount of heat energy required to change a solid to a liquid or a liquid back to a solid. Then we have latent heat of vaporization, which is the amount of heat energy required to be added or removed to transform a liquid into a gas or a gas into a liquid. So with that being said, so distillation columns operate in the area of the graph that is represented by latent heat of vaporization, and distillation columns operate under the principle of phase change.
Vapor pressure is very important for distillation because of its physical properties. It's dependent on temperature. It's measured experimentally by bringing a sealed container with a liquid to a specific temperature to where it allows itself to get to equilibrium, and then we're able to measure the pressure by measuring the head space. Fractionization takes place over a temperature and a pressure gradient, and in our case we use it as a packed column, and this served as additional space for the condensation and vaporization to take place.
Typical distillation process involves several key components that work together to separate mixtures based on differences in their boiling points. The reboiler is where we heat up material to provide heat to the column. The column contains stripping and rectifying. In stripping, rising vapors strip out and concentrate the component. In the rectifying section, concentration gradient is set up to maximize the yield in the top of the column. Concentration gradient is set up through fractionization. Once the vapor is at the correct concentration, we condense it out, and at this point, the distillate is either recycled or collected as fire. Typically, columns have 3 modes. The first one is batch mode. In this mode, all the feed is introduced through the reboiler, and the whole column is set up through rectifying. We expect higher yields in batch mode with a fixed column like ours.
The next mode we're going to discuss is continuous mode. In continuous mode, we introduce a feed into the column. Below the feed point is the stripping section, where the volatile component is removed from the feed. Above the feed location is the rectifying section. Here we establish a steady state concentration gradient. A special case of continuous mode is to operate the system under vacuum. This will lower the boiling point of the reboiler and feed mixtures. It uses less energy. And finally, it's often used for substances with high boiling points where temperatures can cause degradation of product.
So the ethanol water phase diagram is also known as the VLE curve, and for our system, vapor liquid equilibrium occurs at 95.6%. It can never exceed this concentration, therefore it's called an azeotrope. The BLE curve can also be used to predict the vapor composition of a polluting liquid. During the distillation fractionation process, we set up 3 different profiles, 2 of which are listed. The temperature profile is hotter at the bottom and cooler at the top, and the pressure profile, where the pressure gradient across the column, the pressure is higher at the bottom than at the top. When the temperature and pressure gradients are set up, the concentration gradient is also set up.
So a material balance can be performed around each component of the distillation system. To ensure we have an accurate material balance, we need to avoid spills when measuring solutions. Also, we need to collect as much heel as possible. Heel is the remnants of the materials after the run inside the system, and our data needs to be reported accurately as well. Here's a block flow depiction of our distillation system, and we will perform an overall and an ethanol mass balance around each component. Reflux ratio is an important parameter that can be adjusted. It is expressed as a ratio, with the first number being the number of parts going to the column, and the second number being the number of parts collected as product. The lower reflux ratios, we have higher production rates because more distillate is being diverted to product collection. We expect lower yields because there is less heat removal at the top of the column, which can lead to less stability in the column. And at higher reflux ratios, we expect lower production rates, higher yields, and more stability.
Here's a quick intro to our distillation equipment that we ran with. Starting at the bottom, you'll have the reboilers where we load our feed into, and then you move up to the pad column, the main part of the system, and to the side of that you have a differential pressure management as well, and that'll move out to the top of the column towards the condenser, and then it'll go through the decanter, and we'll also have a pistol intake, cooling water flow meter, and then the bottom product tank. And then this is a simple PFD of our system. It doesn't go into a lot of detail, but it just shows us material flow paths, and it shows the interconnectivity of all the other equipment.
Next, we'll be discussing some of our general operating procedures. We have 3 phases of our operation: pre-start, operation, and shutdown. During pre-start, we do things like aligning our valves, mixing our solutions, and setting up our computer. Next, in the operation phase, we record initial readings, turn on our reboiler and stopwatch, and turn on the reflux valve to initiate product collection and record our data. If we wanted to run in vacuum or continuous mode, we have steps for that also. Then during shutdown, we turn off all of our components, collect all the product and other solutions. Then we measure the concentration, density, and mass of all the solutions. And then we move on to the cleanup step of the lab. And in the event of an emergency, all power to the system can be cut at the command module. Safety is always a top priority in the lab, and for our experiment, the largest hazard comes from handling hot solutions. To deal with this, we wear proper PPE, including monogoggles and proper gloves. And while working, we keep hot ethanol solutions as far away from our breathing zones as possible. Any spills are cleaned immediately, and our work area is always organized and clutter-free.
So at this point, we would like to present our distillation data. So we followed one operational strategy for all of our labs. We maintained a temperature at the top of the column as close to azeotropic boiling as possible to produce our highest yields as possible. We reduced reboiler power by 5% for every time the top of the column temperature increased by 0.5 to 1 degree Celsius. We collected product for a minimum of 15 minutes, and we recognized and recorded specific operating days and recorded it on our run sheets. During our experiments, we determined the effects of reflux ratio and feed temperature on production rate, yield, and run stability in batch and continuous modes respectively, performed overall and ethanol mass balances, and used molecular sieves to concentrate ethanol solutions.
Our first experiments were batch distillation, and from our project plan, our goals were to determine reflux ratio on production rate and yield, perform a material balance around each major distillation component, including overall mass balance within 5% and overall ethanol mass balance within 10%. To accomplish these goals, our class planned 4 experiments running 4 different reflux ratios. We expected the higher the reflux ratio, the higher the yield, and the lower the production rate. The reason for this being, at a higher reflux ratio, we divert more product to the top of the column, which stabilizes temperature but decreases production. For all experiments, our data was plotted as follows. Blue is the reboiler temperature, orange is the temperature at the top of the column, gray is the pressure drop across the column, also known as delta P, and yellow is the reboiler power. Based on our reboiler curve, you can see that the reboiler slightly increased in temperature as expected. As we remove ethanol from the reboiler, boiling point increases slightly. Our top of the column temperature, we collected product for less than 15 minutes and the temperature couldn't be kept stable. It increased rapidly, going up 2.5 degrees. We truncated the run because we decided that adjusting the reboiler power wouldn't be effective. Our delta P curve, a higher pressure drop means a higher flow rate, and this is where we expected to see our highest production rate. In summary, this wasn't a stable run and it was the lowest reflux ratio that we ran. So this is how we tracked our material balance. We used a block flow diagram and an Excel spreadsheet to calculate a material balance around each component. We performed a material balance for overall mass and ethanol balance. We desired ethanol within 10% and overall mass within 5%. Our ethanol balance didn't close within 10%, and we attribute this to error in hydrometer reading or determining concentration. Another source of error is product till left in the distillate tank because it has a flat bottom. We did close our overall mass balance within 3%, and our primary source of error here is heel left in the receiver, reboiler, and the column.
In run 2, we raised the reflux ratio to 1:1. As you can see, the reboiler temperature increased slightly, as the reasons pointed out earlier. The temperature at the top of the column did not remain stable. Due to this, we were unable to collect product for 15 minutes. If you look at the delta P curve, we have an indication of our highest collection rates at the beginning, and tapered off as the run went on. We were able to close our material balance within our desired limit of 10%. We accredited our success and improvement in our hydrometer readings and calculations. We did not see any errors other than was previously stated.
In Lab 2-1, we increased the reflux ratio to 1.25 to 1. The reboiler curve behaved like the other experiments. We had more stability at the top of the column in this experiment. We made one power adjustment, and that seemed to make everything stable. Our differential pressure curve indicates a steady vapor flow throughout the experiment. Overall, this was the first stable run. In this lab, we had excellent closure on both material balances and are confident in the measurements we made.
These are our Lab 2 data. It's actually a very stable run based on top of the column temperatures. And we increased the reflux ratio to 1.5 to 1. We did observe some slightly higher delta P's, but nothing out of the ordinary. We hypothesized that by increasing the reflux ratio, we're sending more solution to the top of the column, which increases the fluid resistance and then drives those higher delta P's. And then this is the 2-2 material balance. We did end up having a large error, but we assumed that was due to misreading hydrometer
As you can see, increasing reflux ratio led to an increase in yield and decreased production rates, and this is to be expected by the theory we learned. We experienced stable experiments at the highest reflux ratio, and this is to be indicated by acceptable product collection time and product collection closer to the azeotropic temperature. Finally, an increase in reflux ratio from 1.25 to 1 to 1.5 to 1 did not improve the yield that much, but we observed significant loss in production rate. So we recommend optimizing around 1.25 to 1 for reboiler concentration. In summary, changing the reflux ratio followed what was predicted by theory. For our reboiler concentration, we didn't achieve stability until we upped the reflux ratio to 1.25 to 1. And finally, we closed most of our material balances in desired ranges, and when we couldn't, we were able to figure out the errors.
Based on these results, we came up with these recommendations. First is to improve lab techniques, use more than one person for verification, increase reboiler at half a degree instead of 1, maybe consider using a lower reboiler power on our first adjustment, and we should observe to look at the top of the column to check for fluid. We should also optimize around 1.25 to 1 reflux ratio for 10% solution. Our conclusions are that 1.25 to 1 was most optimal. We had good yield and decent production rate. We noticed when we moved to 1.5 to 1, we gave up too much productivity. And we do not believe our column is long enough to set up the proper temperature and concentration to hit the proper AC control. Finally, the experimental results support the theory that increasing the reflux ratio leads to increased yield and decreased production rate. Our lessons learned are follow procedure and valve alignment, verify all the entries on the run sheets, and the only way to get better is experience and lab skills.
And then for lab 3, we had some goals. We wanted to determine the effects of heat temperature on production and yield for continuous distillation. And we wanted to maintain our material balances in the previous experiments. We have an experimental plan, the reflux ratio of 1.25 to 1, and we located the feed for our run in the middle of the column. And we have the heat take, it's about 30–40% power. This is the data from lab 3, and there's 2 more curves in there. You have the heat take curve, and then you have the feed temperature curve. And based on it, it's actually really reliable for our run, but we did have to make one minor adjustment to the reboiler to maintain that constant temperature. And then as the heat in the experiment kind of tailed off, it showed us that the heat take wasn't quite maintaining that temperature for our run. But there were some consistent pressure drops, which show that there's consistent production as well. And then here's our material balance. It closed within our desired limits, really efficient, and that gives us a lot of confidence in our readings and all our prior work.
So the second run of lab 3 behaved very similarly to the previous run, and as you can see, the temperature at the top of the column had a stable feed temperature decline, just like the first run. Delta P was very consistent, and it only needed one reboiler adjustment. And then we were able to close our material balance within our desired limits for our second run.
Here are the results for lab 3. We observed little differences between the experiments. This suggests we didn't increase the power to the heat take enough for this particular flow rate. Since the experiments were very similar, we didn't experience any trends in yield. Here are some observations we made. The stability of both runs indicates a good reflux ratio. The experiments were very similar with no trends observed. We observed a slightly lower yield in production compared to the 10% batch experiment. We attribute this to there being a shorter rectifying section.
So here are our recommendations and conclusions from Lab 3. For our two conclusions, we couldn't draw any specific conclusions because our experiments were too similar to see any trends, but we were able to see that we did have acceptable yield and production rates. So for our future recommendations, we recommend using a higher heat power with higher flow rates and using different reflux ratios and feed concentrations.
Our Lab 3 lessons learned are mainly trace the drain lines and use the balance only for weight.
So here's our experimental results for the heating cohort. For labs 1 and 2, we ran our distillation column in batch mode, and our goals were to determine the effects of reflux ratio on production rate and yield for 2 different reboiler concentrations. We also wanted to perform a material balance on each major component of the system, and we wanted to close our overall material balance within 5% and our ethanol material balance within 10%. Our experimental plan was to run 6 experiments at 3 different reflux ratios and 2 different reboiler concentrations. Our expectations are that when we increase our reflux ratio, this leads to better run stability, higher yields, but with a reduced production rate. Also, increasing our reboiler concentration will increase vapor flow within the column, which will then increase our production rate. So here's our data from lab 1. We plotted the same information as the day cohort for our batch experiments. And for this experiment, we ran a 1-to-1 reflux ratio with a low reboiler concentration of around 5%. If you look at the temperature of the reboiler, we can see it gradually increases as the run continues. This is expected due to our lowering concentration of ethanol within the reboiler. If we look at the temperature at the top of the column, we can see that this was not a stable run. Our temperatures increased near the end, even though we tried to account for that by decreasing our reboiler power. Because of this, we had to truncate the run early, and we were not able to collect 15 minutes of product. If we look at the delta P in the column, for the time we did collect product, this was mostly stable. This just indicates that we had a stable production rate. This is our material balance. So we were able to close our material balance within the limits we set, although the limits on our ethanol were near the upper limit, around 9.5%. We think this is due to our error in our hydrometer readings and also our leftover fuel in our product collection.
In our next experiment, we raised our reflux ratio to 1.5 to 1. And looking at our data, this run was a little more stable. We did not collect product for 15 minutes, despite lowering the reboiler temperature. Also, our pressure drop curve is indicating higher production rates at the beginning of the run rather than at the end of the run. Ethanol variance on material balance was higher than we desired. Our overall balance was within target. We think this is due to measurement errors for one or more of our concentrations.
Our final experiment from lab 1, we raised the reflux ratio to 1.5 to 1. In this experiment, we were able to collect for 15 minutes, but at the end of the product collection, we could see that the temperature at the top of the column still increased. This indicates that the run was a little more stable, or a little more optimal than it looks, but we need to increase the reflux ratio to get the more stable. Looking at the pressure drop curve, we observed more pressure than normal. We think this because we're sending more solution to the top of the column, which creates more resistance to the vapor flow. And then here, both of our material balances flow within the desired range.
So for lab 2, we used a higher reboiler concentration at 15% and the same reflux ratio as lab 1. And looking at the data, the reboiler temperature rose slightly as expected due to the concentration of ethanol in the reboiler decreasing. The temperature at the top of the column was very stable, and the reboiler power did not need to be adjusted. It was a very stable run, and also the differential pressure was higher than previous runs, indicating a higher production rate, and was also very stable. The material balance closed exceptionally well. We believe that we had better technique taking hydrometer measurements and reducing yield in the system.
For the next experiment, we increased the reflux ratio to 1.25 to 1, and that gave us a stable run as indicated by the temperature at the top of the column. Our reboiler did not need to be adjusted, and our delta P was very stable, though lower than in the previous experiment. This indicates we had a lower vapor flow and therefore lower production, which can be expected for higher reflux ratios. The ethanol and overall mass balance both closed within our desired limits, and any errors can be attributed to mistakes when measuring or yield remaining in the system.
In our final experiment for lab 2, we see that the reflux ratio is now 1.5 to 1, giving us another stable run. Plots indicate no adjustment to the reboiler was needed. Our delta P measurements are similar to the second experiment. However, some of the pressure drop was higher due to fouling, or what I should say, local flooding at the top of our column. This is from reflux ratio, causing what we expected to see, a decline in production. Our material balance still closed exceptionally well for this experiment.
Here's our data for labs 1 and 2. At 5%, the trends for yield and production rate did not follow the trends as expected by the theory. We attribute that to the 1.1 and 1.25 to 1 being unstable, where we had lower product collection times. Looking at the current product collection times at 5%, our most stable run occurred at the 1.5 to 1 reflux ratio. By examining the average product collection temperature for this run, it was over 3 degrees higher than the azeotropic temperature for ethanol and water. This suggests we can further optimize and by investigating higher reflux ratios. For the 15% reboiler experiment, we saw yield remain unchanged, and that suggests that the 1-to-1 reflux ratio is very close to optimal, and we should only make small changes around that point. Production rate was lowered as expected by increasing reflux ratios. All experiments were relatively stable, and average product collection temperature was within half a degree of our azeotropic temperature, which was very good.
So here's our observations for labs 1 and 2. At our 5% concentrations, increasing reflux ratio generally decreased our production rates, but did not consistently improve our yields across those different reflux ratios. At our 15% experiments, however, showed much higher yields, production rates, and better column stability. At higher volatility at our 15% concentrations, showed increased vapor flow and production rates, while our yields remained stable across the different reflux ratios. Our material balance closed within the limits we set, and most of our errors being attributed to our hydrometer readings. So some recommendations. We need to run a higher reflux ratio at those lower 5% reboiler concentrations, and a lower reflux ratio at the higher 15% concentrations. We could execute a better analysis on our product for the truncated experiments. We could disassemble our product collection tank to collect the heel that was left over after each run. This would help us close our material balance variances better. We could also execute an experiment where we ramp up our reboiler power. So normally we start at 80% reboiler power and then ramp down from there. If we did an experiment where we slowly ramped up our reboiler power, this may help us with our temperature gradient within the column. Also, maximizing our reboiler concentrations. As you see, we had much better runs with higher reboiler concentrations, better productivity, yield, and it was easier to control the column temperature. We could also inspect the system and control module annually. As you know, we had like a fire at our control module, so we had to delay some experiments. This might help us in the future not have to delay any more experiments. So here's some conclusions for labs 1 and 2. Our first conclusion is that column stability is important for generating data that meets expected trends, and higher reboiler concentrations lead to better production rates and yields. Data indicates that reflux ratio can be optimized based on reboiler concentration, and higher reflux ratios are necessary for lower reboiler concentrations. Some lessons learned: show up prepared, review project and experimental plan often. We can sometimes recover an experiment if an error is made. Look for subtle changes in operating conditions and report them, and independently verify measurements when possible.
In Lab 3, we investigated continuous distillation. Our goals were to determine the effect of feed temperature and location on product rate and yield for continuous distillation. We were only able to run the middle location, however, the 1410 class ran the bottom location, and we're going to look at that information as well. Our experimental plan was to look at the reflux ratio of 1.25 to 1. This was determined from the day cohort when they ran a 10% reboiler solution. Our feed concentration was approximately 20%. Feed location for our experiment was in the middle. 1410 class operated at the bottom of the column. Our heat tape settings were 30, 40, and 50%. We expected that increasing the feed temperature will increase the production rate due to increase both vapor flow rates. In our first experiment, we had a heat tape setting of 30%. If you look at the experimental data, you'll see the 2 additional curves. There's a heat tape temperature, and there's also a feed temperature. Looking at the curves, it appears that the experiment was stable based on the minimal rise at the top of the column. We did have to make one reboiler adjustment. According to the pressure drop curve, we had a higher production time, or a higher production in the beginning of the run. And then we close all our material balances in the desired range.
So for this experiment, we forgot to increase the heat tape power to 40%, and we ran at 30%, but our heat tape temperature did rise. The data was incomplete though, since we started to record that temperature late. But overall, the run was stable, as indicated by the temperature at the top of the column. We adjusted our reboiler once, and the pressure trough was fairly constant for the whole run, as indicates a consistent production rate. And this is our mass balance for the run, and once again, it did close where we expected it to.
In our final experiment, we ran at 50% heat take power. The run was stable. However, we noticed the feed was both liquid and vapor going into our column. The feed temperature was above temperature at the top of our column. We only adjusted the reboiler one time, as we did with the first 2 experiments. The pressure drop was higher at the beginning of the product collection due to higher feed temperatures at this time. But our material balance goes within the desired range of variances for this experiment.
So here are the results for our class where we ran feed at the middle of the column, and the 1410 class ran their feed at the bottom of the column. When feeding at the middle, our best yield was obtained when our feed temperature was lowest, and better production rates were observed for higher feed temperatures, which was expected due to higher vapor flow rates. And the average product collection temperature was consistent for all feed temperatures. We thought that feeding at the bottom of the column would lead to higher yields because the whole column would act as a rectifying section, but we did not observe that, however.
looking at our lab 3 observations, there's good column stability for all experiments. The average product collection was very consistent for all experiments, so was the average product temperature. We observed our highest yield when feeding in the middle at the lowest feed temperature. When we fed at the bottom of the column, we had the highest yield at the highest feed temperature. Having a mixed feed led to a reduction in yield and production rate. And for recommendations, we think that for continuous distillation experiments, we can optimize the column operation by further investigating parameters like feed temperature, feed rates, feed locations, and our feed concentration.
Our conclusions are it's best not to operate feed temperatures higher than the top of the column. Lower feed temperatures are optimized in the middle of the column, and our higher feed temperatures are optimized when feeding at the bottom of the column. With batch and continuous processes, 1.25 to 1 reflux ratios work well with 10% reboil solution. And our lessons learned are to understand and follow procedures as well as the experimental plan.
And here we have to combine data for batch on both the day and the evening cohorts. So we concluded based on the data that there's an optimum reflex ratio that could run based on the concentration of ethanol in the reboiler. And then for 5% specifically, we want to recommend exploring higher options of 1.5 to 1 above that. And then for all the other concentrations, we kind of want to go more specific and find slightly lower or slightly higher concentrations. And just so we can fully optimize whatever's in the reboiler.
We explored using commercially available sieves to concentrate the ethanol above the azeotropic concentration. We set up 2 experiments, one stirred and one stagnant, using literature values for molecular sieves to ethanol solution masses. Here are the experiment results. We generated a 96% ethanol solution from absolute ethanol. We added 10% excess mass of sieves based on literature values. We measured the concentration in 30-minute intervals over an hour and a half. As you can see in both experiments, we removed 33% of the available water. From the results, we concluded stirring made no difference. The age of the sieves were less effective than the literature states, and we recommend tripling the mass of sieves for future experiments. This concludes our talk. Any questions?
So you guys mentioned you had questions with reading the hydrometers. Were the readings all taken at the same temperatures? I was curious. Solution temperatures all the same? Yeah, when you were reading your hydrometers, were you taking them all at the same temperature?
We applied the temperature correction. We had a chart that showed us. I think our main problem was trying to see the line. We looked above it, we looked below it.
Okay.
We figured it out in the end. That is.
Anything else? All right, very good, folks. Thank you. Okay, so when we had our little oops with our equipment, the day cohort chose to use the reactor module in the lab and do some experiments with it. So I gave them a little project plan, and as a class we developed a little experimental plan for them to execute 3 labs with. And so let's go ahead and bring those members presenting that up here. our presenters. So in this, our experimental, our project plan was to operate two different types of reactor, a batch reactor and a plug flow reactor, and to look at activation energy as well as rate constants and calculate those for both types. In the plug flow, we also looked at the effective residence time on extended reaction for fractional conversion.
We'd like to start out with some background and theory on reactors and kinetics. Before we dive deeper into chemical reactors, let's go over some key terms. These definitions will help us better understand the concepts that we talk about throughout the presentation. I'm highlighting a few of these terms, but all of them are important and we'll discuss throughout the presentation. We have steady state, which is that process inputs and outputs remain constant in continuous operations. In the non-steady state, process inputs and outputs are constantly changing. Kinetics is science regarding the rate of chemical reaction proceeds, and the mass transfer is a phenomenon where chemical reagents are mixed together. Rate constant is proportionality constant in a rate equation. The reaction rate is how quickly a reaction proceeds. Yield is a percent of the desired product forms from theoretical maximum possible. And the saponification reaction is a type of reaction between an ester and a base.
So there's several types of reactors. The first we're going to be talking about is an isothermal batch reactor. They're closed vessels. They're very homogeneous reactors. These reactors have some means of heating or removing heat, and they're stirred with some form of agitation. And they're non-steady state reactors, so reaction rate and extent of reaction varies over time. The next type of reactor is a CSTR, or a continuous stirred tank reactor. And it has similar features to a batch reactor, except feed and product are continuously fed and removed. And these reactors can be placed in series, and they're also steady-state reactors. The reaction rate and extent of reaction are determined by the amount of time the reagents are allowed to react. This is called space-time. Another type of continuous reactor is a plug flow reactor. This is a tubular reactor in which reagents are fed into one end at a specific flow, and it leads into individual reactant plugs traversing in the reactor. And the concentrations of the reagents within the plugs constantly change, but reach a steady state at the reactor exit. The amount of time each plug remains in the reactor is called residence time. Here's some examples of reactors. Going from the left to the right, you can see another batch reactor that can be run as a CSTR. And the next is a cascaded CSTR. And the bottom two are plug flow reactors, and the plug traversing a reactor on the bottom right.
In discussing reactors, it's important to discuss the difference between mass transfer and kinetics. Mass transfer ensures uniform reagent mixing throughout the reaction. Reaction kinetics are driven by molecular collisions and influenced by temperature, pressure, and concentration. And product buildup reduces reactant concentration and slows the reaction. Engineers and scientists use the rate law expression to mathematically explain how quickly a reaction proceeds. Rate law determines how fast a reaction occurs. Reaction orders and rate constants must be determined experimentally. Here's an example of a rate law for a particular reaction. Please note that our reaction is a rate of change of concentration. The change of our reagents is multiplied by a rate constant, and our concentrations are raised to a power, which represents our reaction orders. A reaction order is determined by how the concentration of the reagent influences the overall rate of reaction. A zero order, rate is unaffected by reagent concentration. A first order, rate doubles when reagent concentration doubles. Second order, rate quadruples when reagent concentration doubles. The second table refers to some examples of reactions of a particular order. Our experiment focused on a second order reaction as listed on the table. This means that the change in concentration in both reagents affects the reaction rate. line that we experimentally determined the rate constant, which we will find out that is later influenced by temperature. Rate constant K is dependent on temperature and is determined experimentally. Units for K vary by reaction order. We use the rearranged rate law to solve for units algebraically based on the overall reaction order.
The reaction that we studied was the saponification of ethyl acetate and sodium hydroxide. Right here, this mechanism, it shows a hydroxide ion attacking a carbon of the ethyl acetate, which then it forms an intermediate. That intermediate is in equilibrium with the reactants, which can either revert or proceed to the product. The forward reaction right here is favored by the longer arrow that you can see. The two intermediates will ultimately proceed to the product. So something about this reaction, it is a well-studied second-order reaction, and that means that the reaction rate will be influenced by the concentrations of ethyl acetate and sodium hydroxide. So by looking at the mechanism, the reaction rate is influenced by the reverse reactions of an intermediate and the shape of the molecules, which limits the attack of the hydroxide ion to start the reaction. So to find the rate constant and the activation energy, we first need to analyze this batch reaction. Our reaction stoichiometry was for every 1 mole of ethyl acetate, it reacts with 1 mole of sodium hydroxide. So we only need to track the sodium hydroxide consumption to determine the reaction rate and the rate constant. So for the remainder of this presentation, we're going to represent C sub A infinity as the initial molar concentration of the sodium hydroxide. We're going to represent X sub A as the conversion of the sodium hydroxide, the concentration of the sodium hydroxide at time n as C sub AN, and the initial concentration of the sodium hydroxide as C sub AO. So concentration plot versus time data for sodium hydroxide, we can determine the rate constant. Our reaction is second order, and the rate expression is rearranged into a linear form. So if we plot 1 over the concentration of sodium hydroxide versus time, it will give us a straight line. So the slope of the line will ultimately equal K. Even if our reaction order is unknown, the linear plot will confirm that it's a second order reaction. And here's an example of the plot that we just discussed. Notice how the y-intercept is the initial concentration, and the slope of the line is equal to K.
The next calculation we were asked to do is for activation energy. The definition is the amount of energy we need to supply to initiate the reaction. For instance, when we strike a match, the energy is provided by the friction of the match struck across the rough surface. Without that energy, the match doesn't light. We derive the activation energy from the Arrhenius equation, which is another expression for rate constant. The rate constant is equal to the Arrhenius constant, which is unique to the reaction multiplied by the logarithmic E raised to the activation energy divided by the universal gas constant at absolute temperature. If we determine several values for K at different temperatures, we can rearrange the Arrhenius equation into the equation of a line, similar to what we did previously. Therefore, the natural log of K can be plotted versus the reciprocal of absolute temperature for various temperatures. The activation energy can be calculated from the slope, and the Arrhenius constant can be calculated from the y-intercept. Here you'll see a graphical representation for solving the activation energy and the Arrhenius constant if we multiply the slope by the universal gas constant. We get the activation energy, and if we raise E to the y-intercept, we get the Arrhenius constant.
So we studied 2 types of reactors, which was a batch reactor and a plug flow reactor. We need to go over some terminology for the plug flow reactor. Residence time is how long a reaction plug will stay in the plug flow reactor, and that's determined by adding the volume of the reactor and dividing it by the volumetric flow rates of both A and B. So another term that we need to define is fractional conversion. In this case, our fractional conversion is merely the amount of sodium hydroxide that we consume divided by its initial amount. So So for rate constant, literature gives us the following expression for a second order plug flow reactor. Therefore, plotting residence time versus fractional conversion term gives us a straight line. The slope of the line equals the rate constant times the initial concentration. Here's also a graphical example, and we determine the rate constant by dividing the slope to the initial concentration. And since we're tracking sodium hydroxide over time, there's a linear correlation between conductivity and concentration. This is lambda, what's at the bottom right there, and it represents conductivity at different times. This is some of the equipment we use. This is our isothermal batch equipment. It's a star jacketed vessel where we keep a constant temperature bath circulating around it. The program interface on the right there, and it has a built-in data logger which tracks conductivity versus time. And this is our tubular or plug flow reactor. Notice we have two reagent pumps. The reagent flows from their source containers into the reactor and is surrounded by a constant temperature bath. They are mixed at the bottom of this coil right there, and the conductivity at the exit is measured. And here's another program interface on the right. And you can see we can input feed rate and our bath temperature. And in similar fashion, it tracks conductivity versus time. And this is some of the operational safety. The main thing is that we're using chemicals with reagents. We want to protect our eyes and skin from hazards, so we'll wear glasses, goggles, gloves, sleeves while handling it in the lab.
Now we will discuss our experiments and results. Based on our project plan, we made our experimental plan in class. We conducted 3 labs. Lab 1 is an isothermal batch reactor at 3 different temperatures with an initial concentration of 0.1 molar. Labs 2 and 3 were our plug flow reactor at 2 different temperatures and 3 different flow rates. Here's our batch reactor procedure. Some of our key steps: set up software, add sodium hydroxide and ethyl acetate, monitor conductivity and temperature. We maintain reagent mass using 950 milliliters of sodium hydroxide and 50 milliliters of ethyl acetate. These volumes were modified from the manufacturer recommended volumes to manage initial temperature. Our procedure for our plug flow reactor: prepared and stirred solutions and ensured correct temperature. We started reagent feed and recorded steady state conductivity and temperature. We cleaned the reactor with the mineralized water at the end of the run.
So here's our results from the isothermal batch reaction. Notice that we ran 3 different temperatures, and notice from the plots, concentration versus time, all 3 plots were linear, which confirmed we had a second order reaction. Also notice that the value for the rate constant increased with temperature as expected, and supports the theory from the Arrhenius equation. Further discussion of our results, notice that we demonstrated that this reaction was second order. Notice the plots were linear, and looking at our data for all experiments, we noticed that the concentration for sodium hydroxide was half, and the reaction rate was approximately quartered. The values for our rate constant increased with temperature, and this is expected with the Arrhenius effect. Despite having the same initial concentration for sodium hydroxide, for each experiment, we noticed that the initial conductivity increased as temperature increased. This suggests that there is a lack of temperature correction built into the conductivity probes. We suspect that even though our plotted information was linear, there could be an offset in the slope value and the sum error and the rate constant recalculated. Our temperature remained very consistent throughout the run, so we think the procedure change from the manufacturer was very beneficial. Here's our plot to determine activation energy. From the plot, we calculated the activation energy is 35 kilojoules per mole. The activation energy, 35 kilojoules per mole, appears to be low when compared to literature values. The 2 possible errors is the temperature correction in the conductivity probe, and possible errors when mixing our reagents.
On
this slide, we're exploring the relationship between reaction rate and conversion rate versus time. Early reaction rate is strongly affected by temperature, and later stages are more influenced by concentration. Most of the conversion occurs within the first 6 to 7 minutes. Higher temperature leads to a higher conversion rate, consistent with the Arrhenius equation prediction. Here are results from our labs. At the start, reaction rate is primarily influenced by temperature as seen by the wider spacing of data points. After the initial period, concentration becomes the dominant factor influencing reaction rate, shown by the closer data point spacing. Both reaction rate and fractional conversion increase with temperature consistent with the Arrhenius equation. Higher rate constants, K values, result in faster reaction rates and greater overall conversion. Here are conclusions and recommendations from our batch reactor. Some conclusions: we confirmed that we have a second order reaction. Conductivity issues could impact K values and activation energy. Some recommendations: use temperature corrected conductivity probe, improve pipetting accuracy, run duplicate trials with varying temperatures and concentrations.
So we ran the same flow rates and concentrations for 2 different temperatures. We also achieved 3 different residence times. Our first experiment was at 25 degrees Celsius, and we obtained a linear plot and determined that our rate constant was 0.03 liters per mole per second. Our second experiment here was at 30 degrees Celsius. We obtained a rate constant 0.052 liters per mole per second. And notice that the value of the rate constant increased with temperature. And this, again, with the linear plot, confirmed that this was a second order reaction. So here you can see the increase in temperature means increase in conversion. We increase conversion levels off as residence time increases. Our optimal residence time for the temperatures we ran were between 400 and 500 seconds. Our plots to calculate our rate constants were linear, which indicates it's a second order reaction. Being linear gives us confidence in the data we collected. The rate constant values increase with temperature as expected. Our conversion increase with temperature is expected as well. When we notice residence time increases, our conversion levels off. This indicates that we can have an optimum value for residence time, and subsequently, we can optimize reactor design for volume and flow rate. Here are some of our conclusions, recommendations, and lessons learned from the tubular reactor. We confirmed second order reaction and conversion increases with temperature. There are 400 and 500 seconds of residence time, and residence time versus conversion is an important design criteria. Make sure you confirm your calibration curve prior to using the reactor, and rinse and clean equipment after use, and operate at various temperatures, concentrations, and residence time. Make sure to read and understand procedure prior to use as well. Are there any questions?
Which type of reactor did you find to be the easiest to work with?
In my opinion, it was the batch. We had less problems with it. So, in my opinion. You can ask them.
Oh no, I like the flow a lot.
So why do you like
It's easier to start up, I feel like. With the batch, we kind of start the timer in order, and sometimes we did it out of order, so they kind of interfere with our experiments. But overall, I like both of them, but I think flow was a little bit better.
Okay, I'm closing Q&A. Okay, so the evening cohort ran the friction loss in piping systems experiments. And again, we had had to shift gears, but we got it done, and they did a fairly good job. At this time, I'll bring up the presenters the friction loss and piping systems. There they are. And looking at this one, we have a pretty versatile pipe stand that has various valves, fittings, flow measuring devices, and a pitot tube and other things. And so we designed a project plan around 6 of these things, as you can see up here. So we looked at friction loss in horizontal pipe runs, friction loss in valves and strainers, and then we evaluated an orifice and a Venturi flow measuring device, as well as we traversed a pitot tube to get a velocity profile in a pipe.
Background and theory when it comes to friction loss in piping systems. Basically, it describes pressure or energy decrease as fluid flows through a pipe or system due to friction. The loss is primarily caused by the viscosity of the fluid and source roughness of the pipe. Some of the important terms we'll go over and discuss further later on. Fluid, Reynolds number, friction factor, as well as Venturi, orifice, and laminar flow.
All right, now we're getting the fluid flow. Fluid flow is the conveyance of material to many chemical operations, including heat exchanging equipment, distillation columns, and separation tanks. Fluid flow is useful in understanding system operation and being able to approximate the response of fluid systems. A fluid has no fixed shape. It conforms to the shape of its container, and a fluid can be a gas or a liquid. Now velocity, basically how quickly a fluid is traveling. If the fluid is closer to the wall, the velocity would be practically 0. If the fluid is towards the middle, it's going to be almost maximum velocity. And you can get the average velocity by taking the volumetric flow rate divided by the cross-sectional area. And you can also take the volumetric flow rate times the density, and you'll get a mass flow rate. Now the continuity equation, basically mass flow in a fluid system between any 2 points is constant. So mass at point 1 is going to be equal to mass at point 2. And for incompressible fluids, volumetric flow rate at point 1 is going to be equal to volumetric flow rate at point 2.
Here we're going to talk about the energy balance of Bernoulli's equation. Here we're looking at the big picture of fluid flow in piping systems. Factors like elevation changes, friction resistance, compressibility, work done by or on fluid, all the fluids flow. We use something called the Bernoulli equation to account for all these energy factors into one energy balance. The Bernoulli equation is an energy balance where each term represents a form of energy in the system. The first term is pressure energy, the second is kinetic energy, which is velocity, the third term is potential energy, which is height. On the right side of the equation, we use shaft work if the fluid does not do anything, or energy loss is due to friction. All terms have units of energy per unit mass, meters squared per second squared, newton meters per kilogram, or joules per kilogram. It's important to stay consistent in SI units to make sure the equation balances properly. In most of our studies, we focus on solving for friction losses, and we simplify the equation depending on our system setup. Fluids can behave in 3 different flow regimes: laminar, turbulent, and transition. Laminar flow happens at low speed or thick fluids. It is smooth and layered. The velocity profile is conical because of the friction loss of the pipe's edges. Turbulent flow is chaotic or swirling and random movement. This is great for mixing fluids together. The velocity profile is flat compared to laminar. Transition flow is a messy middle ground we try to avoid. It's unpredictable and makes instrument reading very unstable. We're going to talk about the Reynolds number. The Reynolds number and flow regimes. We predict which flow regime we have by using Reynolds number, a ratio of inertial to viscous forces. This is calculated by density times velocity times pipe diameter divided by fluid viscosity, and the number has no units. Some of the key thresholds for the Reynolds number: less than 2,300 is laminar flow, 2,300 and 4,000 is transition flow, and greater than 4,000 is turbulent flow. Designing your pipes for turbulent flow usually helps to maximize mixing and minimize unstable operations. We always want to avoid operating near 2,300 to 4,000 Reynolds number because it's harder to predict flow behavior.
So now getting into friction factors and head loss and kind of continuing on with what Andrew was talking about. We're actually going to be using Bernoulli's equation here to solve for W7F. Now, we can see that we have a horizontal flow with a constant pipe diameter, which actually allows us to cancel out some terms such as kinetic energy, potential energy, as well as force work. Now, this leaves us with a much simpler equation for us to solve for. Now, various other mathematical expressions have been developed for friction loss in pipes and fittings, and this actually is very important for developing a piping system, as it allows you to tell how big of a valve or a pump that you might need in a certain area. Now, head loss in pipes, more specifically looking at the Moody diagram. So the first type of friction loss we're going to talk about is head loss in straight pipes. Now, Darcy and Weisbach developed an empirical expression for head loss in pipes. Now, the overall head loss in the pipes is going to equal some sort of Darcy friction factor. And we can rearrange this equation here to actually solve for F, the Darcy friction factor.
Expanding on the Darcy and Mach equation, an engineer named Kohler developed a relationship between friction factor, Reynolds number, and pipe roughness. For laminar flow, the friction factor is simply defined as F equals 64 divided by the Reynolds number. Following that, Wallace developed a relationship for smooth pipe and turbulent flow. In the turbulent flow regime, we solve this equation for various Reynolds numbers and roughness factors in the Kohler equation. On the diagram, the friction factor is plotted versus the Reynolds number for various roughness factors. Laminar flow line is also captured on the diagram, as is the Belize expression for smooth pipe. Notice that there is a region of complete turbulence where the friction factor is solely determined by the pipe roughness. In our summary for the Moody chart, it is derivative from imperial equations. The log of F is plotted versus the log of the Reynolds number. It does vary at roughness factors, while F is solely based on the roughness factor under complete turbulence regime plot. There is no calculated data in transition flow. We did expect erratic results, as we generally don't operate as we stated before. The roughness does not factor in laminar flow. It will always be the same 64 divided by the Reynolds number.
Now we're talking about head loss and valve/fittings. We're introducing the K value, which is basically the resistance value. It represents velocity as they're lost as fluid passes through. These values are experimentally determined, and you can determine these values by head loss due to friction equals K times V squared divided by 2G. You can also estimate total head loss in pipes by taking the sum of piping terms and the sum of the fitting K values and multiplying them by V squared divided by 2G. And these can be used for pump designs. Now we're going to talk about our equipment. We have a pipe stand that has pressure capture on each type of pipe, valve, and fitting, a digital hydraulic bench, basically a tank with a sub pump that pumps fluid at a constant rate throughout our system. We have a piezometer, which basically 3 manometers, measures on what inches of water column on inlet outlet side. Our pipe stand capabilities, we've got valves, pipes, several flow measuring devices, as well as strainers, and all of these we will test later on. Here's our pipe stand. You see it's got 3 circuits, the different valves. It's got a pressure gauge for high pressure drops that measures to a couple bar. And here's our piezometer on the right. This is the schematic, shows where all the pressure taps are and everything's numbered, so you know where to plug everything in at to make sure you're testing the right stuff in the system. It's the manufacturers, and it helped us a lot during this experiment. And this is the hydraulic bench, and it also has the low flow meter to see how much water is pumping into our system in gallons per minute.
We're going to talk about the procedures to measure head loss, piece meter, and gauge. We developed our own pressure measuring procedure after tweaking what the manufacturer gave us. Two of the main points in the procedure are to make sure you clear out all the air in the lines, and don't touch the lines when taking measurements. Those are up there in the bold. Following these main points helps to get accurate readings. The rest of the procedures up there, if you'd like to read it. Here's the procedure for the pressure measurement for valves with the piezometer. This is the procedure for measuring pressure drops across valves. This was developed with much trial and error. Here's the procedure to switch from piezometer to gauge. The piezometer went out of range. We switched over to using a pressure gauge to get more accurate readings. Then we converted those gauge readings into meters of water to stay consistent.
Now we're going to get into our experimental results. Start with experiment 1. We were looking for the friction losses in straight pipes. Now, our goal here was actually to study the friction losses in smooth and rough pipes at various diameters, and we were going to compare those results to the Moody chart and the Blasius friction factor. Now, our procedure is actually pretty simple. Basically, we just wanted to flow water through the specific circuit that we were wanting to test, and for each pipe, we were going to collect the differential pressure and the flow rates at various rates. Now, we use that to determine and answer all the questions below, and the procedure is also something that we use for various of our other experiments that we will have to see. Now, starting with the first pipe that we tested, it is a 13.6 millimeter diameter pipe. Now, looking at the Darcy friction factor and the Blasius friction factor, we can look at the numbers and tell that they are very similar, and we plotted those over here, and we can use this to determine that it is actually smooth based on the little difference between the two lines. Now moving on to the 17 millimeter pipe, we had very similar results as we can see looking at the Darcy factor and the Blasius friction factor, as well as looking at our curves. Finally, with the 26.2 millimeter pipe, we also determined this one to be smooth as well, based on our results given to us in our comparison by the graph. Now, for the 14 millimeter pipe, we had something a little bit different. This was actually a predetermined rough pipe. Now, we can see over here on the graph plotted by the yellow dots, we can see that we have a roughness factor of 0.35 to 0.4, and we also have the smaller pipes plotted down below as well. Now, we determined all three of the PVC pipes are smooth. However, the 26.2 millimeter pipe may have a slight bit of roughness, but it's hard to tell an exact value just to too many KD lines emerging where the data is plotted. Now, our KD value we estimated ranged from 0.036 to 0.04. And based on the results that we came up with, we can conclude that the Moody chart and the Blasius equations are effective means of measuring friction loss.
Our second experiment is friction loss of strainers. Our goal is to determine head loss in both pipe strainers, both coarse and fine, and then calculate the K value for each strainer. The procedures for this experiment really didn't change from prior. We then had to pilot several analysis points and then evaluate data. Here are our strainer results. As you can see from the drawing, if we plot flow rate versus delta P, K value versus Roane, there's really no difference between the two strainers tested. This may be due to equivalent flow areas between both strainers. Strainers can fill with some type of media, dirt or sand. The fine strainer will exhibit, we believe, more friction loss than the coarse strainer. Reviewing our results for our strainer experiments, we noticed very little difference between coarse and fine strainers with respect to friction loss. We hypothesized that if we loaded the finer strainer, that there would exhibit more friction loss than the coarse strainer. We recommend testing with media and strainers to evaluate this. Since the strainers are evaluated, we had a class discussion about how we can use these and think they can be used in series or parallel, depending on the media they're looking to capture. Finally, for our system, we need to operate at the lowest flow rate to minimize head loss. We observe higher head loss at higher flow rates. This is mostly due to dependency of the squares of the velocity, the friction loss, versus the K value having less of an effect.
For experiment 3, we're going to determine K factors for fully open valves at various flow rates, basically head loss and fully open valves. We collected delta P plus flow rate data for this experiment, and we're going to determine the performance of the valves based on the data that we collected. Here are our 3 valves. The ball valve, we expect the least amount of change in flow patterns due to its fluid passes freely through the opening. The gate valve has an indentation where the gate seats, so at lower flow rates we expect higher friction losses due to that. The globe valve has the most tortuous path, so we are expecting higher friction losses for the globe valve. These are our results. So as you can see, the ball valve and globe valve were pretty linear, and the gate valve at lower flow rates had higher friction losses due to where that gate seats. So the gate valve has higher K at lower flow rates. And this is basically a discussion based on the results you've just seen. So the globe valve had the highest friction loss / K value. The ball valve had the lowest friction loss / K value. And the gate valve was similar to the ball valve, but at lower flow rates and higher friction losses due to the indentation where that gate seats. So the K for the ball and the globe were pretty constant, and for the gate valve, it was constant at higher flow rates, but not at lower flow rates due to where that gate seats at.
For this experiment, we used the same valve but only partially opened the valves. We measured head loss and calculated K values at different openings. We were able to plot percent open versus K value to see which valves are best for adjusting flow. This is a graph for the partially open ball valve. As you can see, when the ball valve is more than 50% open, there's very little friction loss. Almost full flow continues. However, once you start closing past 50%, head loss increases dramatically, flow drops rapidly. Based on this graph, if you want to throttle or adjust flow, do not close the ball valve past halfway. It becomes very inefficient. This is the graph for the partially open gate valve. As you can see by the graph, the gate valve does not give good flow control. Even when the valve is almost closed around 8%, flow stays above 90%. This tells us that the gate valves are basically on-off switches, so trying to throttle with the gate valve won't work. This graph is for the partially open globe valve. Based off this, globe valves are the best choice for adjusting flow. Even open only 8%, we were able to cut the flow rate to about 63%. And with further closing, we can control it down to around 20%. As you close the valve, the K value increases sharply, especially from 8% to 2.8%. So globe valves get fine control, but generate high friction loss that close too much. Here's a summary of our results. The best valve for adjusting flow is the globe, then the ball. Gate valves are really bad for throttling. Ball valves should not be closed more than 50% to avoid high friction loss. Globe valves shouldn't be closed less than 8% down to the rising friction and inefficient operations.
So moving on to experiment 5, we actually tested some flow measuring devices. More specifically, the venturi tube and the orifice plate, in which the schematics are right here, as well as the governor equation for the flow. Now, our goal was actually to use the equation to calculate flow rates using the orifice and venturi, and then compare those to what we got from the hydraulic bench. Now, the procedure we did use is shown below. It's a little bit different than the previous ones that we had. Now, we maintained the same flow rates so we could compare flow rates from the hydraulic bench to the calculated flow. And we measured in multiple flow regimes in which the turbulent flow was actually more accurate, showing less than a 3% difference, which increased as we moved into a transitional and laminar flow. Now, to summarize, although the orifice measured actually in transitional flow, we recommend to operate both devices in the turbulent flow, and we determined that these flow meters are good and inexpensive options for flow meters. They can also work in many different hazardous areas that digital flow meters can't actually work in. And finally, we determined that our results support our measurement techniques.
For our final experiment, we will determine the velocity profile and turbulent flow with a Pinot tube. The Pinot tube measures flow velocity by the equation on the right. Velocity, delta V, density, must be known to calculate. Our goal was to traverse the Pinot tube off the center of the wall, take our delta V measurement and convert it into velocity, and then plot a velocity profile. As you can see, we have a flat profile, which is typically of turbulent flow. We expected it to be flatter with increasing flow rates. When we got 2 millimeters from the wall, effects were then noticed in our velocity. We then had more viscous forces taking effect near the wall. We had more inertial effects closer to the pipe. We think that increasing the flow rate will flatten it more and dismiss all effects.
Now let's get into our overall conclusions. So the Moody chart and resistance K values are good tools for engineers to design piping systems. Most systems operate best in the turbulent range. Flow valves are better for throttling. Ball valves should not be throttled, and gate valves are best when operated fully open or fully closed. The orifice or venturi tubes are inexpensive means for measuring flow, and a turbulent flow profile is generally considered to be flat. So some recommendations: we need to procure a means to measure very low delta P, and we also need to place a valve at the end of a system discharge instead of using our hand, and that's our recommendations. Lessons learned: so inaccurate measurements for smaller head losses are going to lead to larger errors. This is just some pictures of all of us. We had fun. I would like to acknowledge our program director, Ms. Laura Hoffman, our program advisory board, our program instructors, as well as our laboratory volunteer. I want to thank everybody for coming out today. Does anybody have any questions?
All right, you may get to pawn this one off on your previous cohort group. So after you've learned your turbulent and laminar flow, which region would you rather operate your tubular reactors in, laminar or turbulent flow? What do you think?
Turbulent.
Why?
So you have more turbulent reactors with more reactions without a reactor.
Mixing, right? Turbulent mixing.
Get the same resonance time too for all of the fluids. Okay, good.
Also good for heat transfer too, right? You want mixing, right? You must have that stuff moving around in there. If you're laminar and you're trying everybody up here. You can stand in front of the screen. So at this point, you can see we have a wide range of ages, personalities, and everything. People with families, people with jobs. Everybody here has made a tremendous work-life school balance. That's the thing. And I'd like to congratulate everybody. They did a very good job in the lab this semester. Very inquisitive group. I like that. Challenged me quite a bit, which I also enjoy. Keeps me on my toes. Really, I saw good progress over the whole semester. They, they always start out a little raw, but after a couple weeks, they come a lot more prepared. They know what they're doing. They understand what it means to take measurements, and anytime that they're asked to record something, it means something to somebody. And so we drilled that all semester. I think they've come away with that. Very proud of them. And I just wanted to say congratulations to our Capstone graduates. Let's give them a round of applause.
I'm sorry, Laura. I was going to say, before everybody scatters, definitely want to get a picture of this group and our board members, our board members and industry partners that are here. I'd love for you, if you're okay with me taking your picture and sending it, if you would join them with it, the Capstone card, if you join me with the picture, and let's grab that for us. We surely appreciate it. We appreciate you being here to support those students. Laura?
Thank you. So one more thing. Professor Dave Chekalot has been with us for quite a while and has been doing the Capstone labs and Jet 1410 labs. And he's moving to Florida. So I just wanted to acknowledge him for all that he has done for us as a phenomenal instructor. So thank you so much.